Okay, so it's my intent that you do section 5.1 after you've done 5.3 and 5.4. Seems to connect better in my opinion. What we're doing in section 5.1 is we're going to start the definite integral, the ideas of it and where it comes from. And the definite integral, one of the places where it comes from is from the area under a curve. So we're going to be approximating the area under a curve. Okay, so suppose we have a curve now and we want to find the area under this curve. We can begin by making an approximation with just one rectangle. So take a moment, pause the video, and draw one rectangle on the graph that has approximately the same area as the shaded area. Now, if you're going to draw a rectangle that has approximately the same area as the shaded area, then it really wouldn't make any sense to make a rectangle that had any other width other than the distance from A to B. So we're going to make our width go from A to B. And then it really would make no sense to either stop below this here or go way up here. That would clearly be an overestimate. I'm sorry, an underestimate. And this would clearly be an overestimate. So what we want to do is we want to stop somewhere so that this upper part of my rectangle hits the curve, right? And so if we stop anywhere along where it hits the curve, then the height of my rectangle can be found by taking some number in the interval, c, and plugging it into the formula, f of c. So the distance from here to here is f of c. Now, there's lots of different rectangles that you could pick. Here are some special ones. We could pick the midpoint, right? So right in the middle of A and B is right here. This is the midpoint. And we can make it so that our rectangle gets its height by putting the midpoint into the formula. And so this is the point, let's call this C comma f of c. And the height of the rectangle, the distance from here to here, is f of c. And so then the area is the width of the interval, the distance from A to B, which the way we find distance is by taking B and subtracting A. Take the number on the right, subtract the number on the left, and then multiply it by the height, f of c. And there we go. Now, we could also use the left endpoint, right? So to get the height of our rectangle, we could take our left endpoint on the interval and go all the way up to the curve, and then go across, and then come down. Or we could use the right endpoint. For us, what we're going to do, even though your book is going to refer to both the left endpoint and the middle endpoint, we're going to ignore those restrictions throughout our work, and we're just always going to use the right endpoint, just for simplicity's sake, right? And so we're going to take the right endpoint, go up to the curve, go across, come back down, and this is the area that we're going to use to approximate. Now, obviously, that's not that close. You can see that we're missing some of this area, and we have a lot more of this area over here that's part of the rectangle that's not part of the curve. So this is clearly an overestimate, but we're not going to try and do this with only one rectangle. So the fact that this rectangle is not very accurate is not going to be of too much importance to us. So using the left or the right or the middle is not really going to matter too much. Okay, so use 4 rectangles to approximate the area under the curve. F of x equals x squared plus 2 over the interval from 0 to 2. Okay, so So that's how we're going to get a better approximation. Rather than trying to do it all with one rectangle, we are going to do it with more rectangles. And in this case, we're being asked to use 4. So we want to keep this as simple as possible. Later, we'll allow for different size widths because that is the best approach, is to allow for different size widths. But to keep things simple, we're going to make them all the same width. And so we're going to call the width delta x. And delta x we're going to find by taking the width of the entire interval. And we're going from 0 to 2, and the way we find the length of the entire interval is by subtraction. 2 minus 0. And since we want 4 rectangles, we're going to divide that by 4. So that gives us a width of 1/2. Okay, so that means that your first rectangle is going to start here at 0 because we're going over the interval from 0 to 2. And we're going to stop at 1/2. We're just going to go up by 1/2. The second rectangle will start from 1/2 and go to 2/2, or 1. The next rectangle will start at 2/2 and end at 3/2. And then we add one more half to that, and we'll get to 4/2, or 2. To find the height of our rectangle, for us to keep it simple and keep it easy to follow along, we're going to use the right endpoint. So for the first rectangle, we're going to stick the 1/2 into the formula, go up to the curve, and then we'll cut across. And there's our first rectangle. For our second rectangle, we're going to take our right endpoint, go up to the curve, and there's our second rectangle. For our third rectangle, we're going to start at 3/2, go up to the curve, and there's our third rectangle. And finally, for our last rectangle, we're going to start here at the right endpoint, go up to the curve, and there we go. Now we just find the area of each one of these rectangles, add them all up, and that gives us an approximation. We can see that our rectangles have more area than our curve, so this is an over approximation. But here's what this looks like. The first rectangle has a width of 1/2, and the height comes from squaring by putting in the half into the formula, right? So the height, we put the half into the formula and we get 1/4 plus 2. Plus, the second rectangle has a width of 1/2, and the height we get from putting in the 1 in, or the 2/2 into the formula. So we get 1 plus 2. When you put the 1, you get 1 plus 2. Plus the third rectangle, the height is 1/2, and then you the width is 1/2, and the height you get by putting the 3/2 into the formula. So you get 9/4 plus 2. And finally, the last one, the width is 1/2, and the height, you're going to put in the 2 into the formula, so you will get 4 plus 2. So the height is 6. Right? And so then, we can put that into the calculator. and I get 7.75. Okay, so obviously we could do better. And let's move on. Use 8 rectangles to approximate the area under the curve. Right? So now we want to use 8 rectangles. So again, very first thing we have to do is calculate the width. The width is to take the width of the entire interval, 2 minus 0, and divide it by however many rectangles you want to make, 8. And so that is 2 over 8, which is 1/4. So each one is a quarter. So this is 1/4, and now you're just going up by a quarter. So this is 2/4. So then this is 3/4. So then this is 4/4, or 1. But if I write it as 4/4, then the next one's easy, 5/4, and then 6/4, and then 7/4, and then 8/4, or 2. To find the height, we're going to use the right endpoint. So here we'll use the quarter, go across, and then down. That's my first rectangle. For the second one, we'll start at 2/4, go across, and then down. 3/4, and then down. 4/4, across, and then down. 5/4, across, and then down. 6/4, across, and then down. 7/4, across, and then down. And then 8/4 across, and then down. Okay. So now we have 8 terms because we have 8 rectangles. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 rectangles. For the first rectangle, each one of them has a width of 1/4, so we have a quarter. And then the height we get by taking the quarter and plugging it into the formula, which is a quarter squared, 1/16, plus 2. For the next one, we take the 2/4 and plug it into the formula to get my height. The width is 1/4 times 2/4 is a half, squared is 1/4, plus 2. For the next one, we're taking the right endpoint, which is 3/4. The width is a quarter, and then we have 3/4 squared is 9/16, plus 2. Plus the next one is 1, and so then you have a width of 1/4, and then you have 1 plus 2. And then you have the next one is at 5, the width is a quarter. You're going from 4/4 to 5/4. You're putting the 5/4, which is 25 over 16 when you square it, and then you add 2. And then next one is at 6/4, from 5/4 to 6/4, so the width is a quarter. To get your height, you put in the 6/4, so 3/2, 9/4. Plus 2. And then 2 more, 7/4, from 6/4 to 7/4, which is width of 1/4, (49 over 16, plus 2. And finally, the last one goes from 7/4 to 2. The width is a quarter. And the height is, you put in the 2 and you get 4 plus 2 is 6. And there you go. Now we simply plug that into the calculator to figure out our approximate area. And we punch that into the calculator, and we end up with 6.4375. With with 4 rectangles. We got 7.75. Obviously an overestimate. You can see that the error is a little less. With 8 rectangles, we end up with 6.4375, which is less area, and you can see that it's a closer approximation. So how do we get better approximation? We use more rectangles. Okay, so use 16 rectangles to approximate the area under the curve of f of x equals x squared over the interval from 0 to 2. Now, that's a lot of rectangles. So what I'm going to do is I'm going to use summation notation to help me out, and the summation capabilities of my calculator to help me out. But again, we begin by figuring out how wide is each rectangle going to be. Delta x. And delta x is going to be the same thing. 2 minus 0 divided by 16, which is 1/8. And so I'm only going to do a couple of these. So this first one starts here at 1/8. Then 2/8. Then 3/8. Then 4/8. Then 5/8. So then the area we get by the width, 1/8, times the height. And the height we get by taking the right endpoint. So for the first rectangle, the right endpoint is 1/8 and putting it into the formula. So this is the formula right here. So it's going to be 1/8 squared plus 2. Plus for the next rectangle, the width is 1/8. And then you're going to put in 2/8. And again, it works better if you don't reduce here. You're going to square that. Add 2. All I'm doing is putting the right endpoint into this formula right here. Right, so the next one we go plus 1/8. And then you're now going to have 3/8 that gets squared plus 2. And so on. All the way until we get to the 16th one, right? So now we're going to write this in summation notation with 16 rectangles. I do not want to write down all of them because that's going to take too long, but we'll write this using summation notation. And I equals 1, right? So 1 is going to correspond to, the index is going to correspond to which rectangle I'm looking at, the first one, second one, third one, and there's 16 of them. So the top one should be 16. Each term here, you can see that out in front has a 1/8. You can see that inside the parentheses you have something being squared plus 2. Each one of them has that. The something that's being squared is a fraction, and the denominator is always 8. And the numerator is just 1, then 2, then 3, then 4. So the numerator is just I. Now if you wish, you can clean that up a little bit. So this becomes the summation from I equals 1 to 16 of 1/8 times I squared over 64 plus 2. And then I will post a video on how to punch this into your calculator so that you don't have to add this 16 times. So if you can't figure out how to use your calculator, I will post a video on how to use the TI-84 Plus. They've changed, so some of you are going to do something different, but I'll walk you through it right now, and then I'll give you a visual in the video. Okay, so the very first thing you do is you look for the list button. The list button is in blue, so you first have to hit the second key and then list. The top button says stat. You use the right arrow and go over to math, and then since we want to do a sum, you hit the number 5. Then you hit second list again, and you hit the right arrow to go to ops, and you hit the number 5 again for sequence. So add up some sequence is what it should say on your home screen. Some sequence, add up the terms of this sequence. Okay, and so then you put in your formula, and your formula is 1/8, 1 divided by 8, times, and then you have a parenthesis, just like you have it there, x squared. You use x instead of I, divided by 64, plus 2. Then you put a comma, and you tell it what the name of the variable is, x. Then you put a comma, and you tell it what number do you start out for x. You first plug in 1 to get the area of the first rectangle, comma, and then you plug in, then you tell it what number to stop at. You're doing 16 rectangles, so you stop once you plug in an x value of 16. And then when you hit enter, ooh, I forgot to close my parentheses. And the calculator tells me that this is 6.9. And you can see that according to my other two, we had 6.4 and 7.75. So this doesn't make sense because it should be coming down, because if we're using the right endpoint, then this is the area should be decreasing, right? So let me make sure that I punch that in correctly. I must have done something wrong on the previous problem, and it was not that. It should have been 7.1875. Must have forgot a term. And so then that follows the pattern. We started off with a 7.75 area using 4 rectangles. That was obviously an overestimate. We got a better estimate by using 8 rectangles, less error. You can see that. So this portion right here is the error, and you could see that this has less error here. And now by going to 16 rectangles, which I have drawn for you, you can see that there's a lot less error, and we're down to 6.9. 6.921875. Okay, so how do we get a better approximation? Well, we use more rectangles, but rather than using more and more rectangles, what we can do is we can make a formula for the approximate area with n rectangles. So write a series using summation notation for the approximation of the area under the curve using n rectangles. Okay, so this is the exact same thing. It's just now instead of having 4 or 8 or 16, now we want to use n, right? So again, first we have to figure out what is the width. delta x is equal to the whole width was 2 minus 0, and we want to use n rectangles, and so each width is going to be 2 over n. We're doing the same problem, the same curve, but now we're using n rectangles, right? And so then my first interval goes from 0 to 2 over n. Then the second interval goes from 2 over n to 4 over n. You're just going up by 2 over n each time. You just add 2 over n. 4 over n plus 2 over n is 6 over n. 6 over n plus 2 over n is 8 over n. Okay, so there we go. To find my height, I'm going to put these right endpoints into my formula. So the height x squared plus 2. This is the curve y equals x squared plus 2. And so we're just going to put this in over here. And so your heights, when we put in the 2 over n, we'll get 4 over n squared plus 2. The second rectangle, we will then get 16 over n squared plus 2. And then we will get 36 over n squared plus 2, and so on. That's enough to get a pattern, right? And so then the area will be approximately, okay, so the first rectangle has a width of 2 over n, and the height, this height. So 4 over n squared plus 2. Plus the second rectangle, the width is 16, the width is 2 over n, and the height is 16 over n squared plus 2. Plus, for the third rectangle, the width is 2 over n, and the height is this one right here, 36 over n squared plus 2, and so on all the way until we get to n. So now let's write this in summation notation. And so in summation notation, this is the summation from I equals 1 and we have n rectangles, because that's what it says, using n rectangles. So each term represents the area of one rectangle. So our upper limit of summation should be n from I equals 1 to n. And if you look at the terms, you'll notice that they all have a 2 over n in front. They all have a fraction plus 2. And then in the denominator, you have n squared for all of them. But in the numerator, you have 4, then 16, then 36. And that is because those are the squares, but if you notice here, this is 2, 4, 6, 8. You're squaring the even numbers. So it's the 2i squared. Again, I kind of hid the pattern by actually carrying out the calculations. I forgot to not carry out the calculations. Had I just left that as 2 over n squared, 4 over n squared, 6 over n squared, it would have been a lot easier to realize that that's what the pattern was, and then we could have cleaned it up afterwards. And so then this becomes the summation from I equals 1 to n of 2 over n, and then you get 4I squared over n squared plus 2. Now let's check to make sure that this matches with what we did in our previous problem. If we had 16 rectangles and then a sub 16, we would get the summation of 2 over 16 times 4I squared over n squared. 16 squared is 256 plus 2, which we can clean that up, and because the 2 over 16 is 1/8. The 4 over 150 over 256 reduces down to 64. Plus 2. And if we look back, we get 1/8 I squared over 64 plus 2. And so now, rather than having to do this over and over again, if we wanted to find the approximation, say using 1,000 rectangles, we have a formula for it. It's not a closed form formula. We don't have, it has this summation in it, but it's still better than having to do this all over again. And so then this becomes 2 over 1,000 for I squared over 1,000 squared plus 2. And although I wouldn't want to do that by hand, the calculator shouldn't have a problem with that. And so I thought the calculator wouldn't have a problem with that, but the calculator can't do 1,000 rectangles with this problem. 1,000 terms of this nature, my calculator won't do. So next time I will try with fewer rectangles, like 100. But the idea is still there. Okay, so use 4 rectangles to approximate the area under the curve f of x equals the natural log of x over the interval from 1 to 2. So on your test, if you see only 4 rectangles, there's absolutely no need for summation notation. I would say that there's absolutely no need for summation notation for anything less than or equal to 10 rectangles. Once you get past 10, then summation notation is going to make your life easier. So you should know what the graph of the natural log of x looks like. The graph of the natural log of x looks like this. It crosses the x-axis right here at 1, and you're going from 1 to 2. And so then the very first thing you need to do is figure out what is the width of your rectangle, your rectangles. And so since you're going from 1 to 2, 2 minus 1 divided by 4. And so now you have 1/4. Okay, so let me go ahead. So then each rectangle has a width of 1/4. So we'll make that one 1/4, and then 2/4, and then 3/4, and then 4/4. Ooh, I'm sorry, that's not right. 1/4 is not to the right of 1. So it's we should write that 1 plus 1/4. 1 plus 1/4. So you just add a quarter. So this one's 4/4. So this should be 5/4, 6/4, 7/4, 8/4. We're going to use the right endpoint. So at the right endpoint, we'll go up to our curve, come across, come back down. Right endpoint, come across, come down. Right endpoint, come across, come down. Right endpoint, come across, come down. Okay, so then the area using 4 rectangles is equal to, right? So the width of the first rectangle is 1/4. The height we get by putting in the 5/4 into the formula, natural log of 5/4. Plus, that takes care of that area. The area of the second rectangle has a width of 1/4. The height we give by taking the natural log of 6/4. And that takes care of that area. Plus, for the next one, the width is 1/4. Natural log of 7/4. We are using the right endpoint, even though my drawing doesn't look like it. We're going all the way up to that curve. Going all the way up to this curve, stopping there and going across. Still didn't get it. Okay. Natural log of 7/4. And for the last one, we have a width of 1/4, natural log of 8/4, which is 2. Absolutely no need for summation notation. There's only 4 terms. So you can just punch them into the calculator. The natural log of 5 divided by 4 plus the natural log of 6 divided by 4 plus the natural log of 7 divided by 4 plus the natural log of 2. And the calculator tells me that the approximate area is 0.4703 to the 4 decimal places. Should put the 0 out in front. Okay. Again, there's no need for summation notation. You have 8 rectangles, absolutely no need. The width of the rectangle is going to be 2 minus 1. But now you have 8 rectangles divided by 8. And so you're going to get 1/8. So then your graph, if you want a picture of what's going on here, you're going to start here at 1, and you're going to go up by 1/8. 1 is the same thing as 8/8. So the next one is 9/8, and then 10/8, and then 11/8, and then 12/8, and then 13/8, and then 14/8, and then 15/8, and then 16/8, which is the same thing as 2. Now you will have 8 rectangles. And for each one of those rectangles, you take the right endpoint and so then your area using 8 rectangles is going to be, the width is 1/8. The height you get by putting your right endpoint into the formula. So you're going to put your 9/8 into the natural log plus 1/8 natural log of, put in your right endpoint, 10/8 plus 1/8 natural log of 11/8 plus 1/8 natural log of 12/8 plus 1/8 natural log of 13/8 plus 1/8 natural log of 14/8 plus 1/8 natural log of 15/8 plus 1/8 natural log of 16/8, and that corresponds to this one here. And we're done. No need for summation notation. It's going to take you longer to write it in summation notation than it is to just plug it in. The natural log of 9 divided by 8 plus the natural log of 10 divided by 8. Don't forget your parentheses, plus the natural log of 11 divided by 8 plus the natural log of 12 divided by 8 plus the natural log of 13 divided by 8 plus the natural log of 14 divided by 8 plus the natural log of 15 divided by 8 plus the natural log of 16 divided by 8, or 2. Hit enter, divided by 8, and you get that using this, you get 0.429 to 4 decimal places. 0.42, 0.47. Yep, you're decreasing because you have less error. So all that seems right. Okay. Now we do want to use summation notation because now we're up to 16 rectangles and I don't want to do this 16 times. Okay, so again, very first thing we have to do is figure out how wide each rectangle is going to be. Delta x is going to equal the width of the rectangle, the width of the interval, 2 minus 1 divided by 16. So that gives us 1/8. I'm sorry, 1/16. Okay, and so I'm not going to draw them all this time because there's 16 of them. Just want to get an idea of what's going on. We're starting here at 1, which again, since we're going up by a 16th, the best thing to do there is to write this as 16 over 16. And you're going up by a 16, so the next one is 17 over 16, and then 18 over 16, and then 19 over 16, and so on. So then your area using 16 rectangles, the width of each rectangle is going to be 1/16. The first height you get by putting in the 17 over 16 into your formula. For the next rectangle, you get 1/16 is your width. Your height you're going to get by finding the natural log of 18 over 16. And then you get 1/16 natural log of 19 over 16. And then so on. We want to write this in summation notation so that we can use the calculator. And so then we can see that we have 16 terms. So we have the summation from I equals 1 to 16. Each term represents the area of each little rectangle, and there's 16 rectangles, so we have 16 terms. Each term has a factor of 1/16 in the front, and then the natural log of a fraction. The denominator of the fraction is 16, and the only thing that changes is the numerator. The numerator is going up by 1, 17, 18, 19, so we know it has something to do with 1 times n. But we want to start at 17, so if we add 16 to it, and that comes from this 16 right here that we added, then we will be fine. Now the rest is punching it into the calculator. And when we punch this into the calculator tells me that this is 0.4078. That was with 16 rectangles. Okay. And now we want to write a series using summation notation for the approximation of the area under the curve using n rectangles. And again, we're still working with the formula y equals the natural log of x, or f of x equals the natural log of x. And we're still going over the interval from 1 to 2. So the very first thing we have to do is find the width of the rectangles. The width is delta x, and delta x is 2 minus 1 divided by the number of rectangles, which is n. So it is 1 over n. If you need to see a visual, right, so then you're starting at 1, which is n over n, and then you're going up by 1 over n, so it's n plus 1 over n, and then n plus 2 over n, because each time you go up by 1 over n, you just add 1 over n. And so then your area using n rectangles, the width of each rectangle is 1 over n. To find your height, you take the natural log of, for the first one, you're going to take the natural log of n plus 1 over n. For the second one, width is 1 over n. And then the height, you're going to take the natural log of n plus 2 over n plus 1 over n, and then you're going to take the natural log of n plus 3 over n. We're going to write that using summation notation. So this becomes the summation from n equals 1, from I equals 1. The top here is how many rectangles you have. You have n rectangles, so it goes from I equals 1 to n. And then the only thing that's changing on these different terms is this guy right here. You can see that they all have a factor of 1 over n, and they all have a natural log of a fraction, and in the fraction the first term is in the numerator, it's n, and in the denominator it's n. But then we have 1, 2, 3, so that's just I. And there we go. And so now I'll be a little less aggressive and approximate the area using 100 rectangles. No need to start all over. Now we know that n is 100, so we can just go and put 100 in right here. So this will be the summation from I equals 1 to 100 of 1 over 100 times the natural log of 100 plus I, all divided by 100. Punch that into the calculator, and from the calculator we get 0.3898. Rounded to 4 decimal places. Okay, so there's your homework for this section. This homework will be due 1 week from Thursday, and we will have more. Thank you. Have a good night. Stay safe.